All right, so now we're going to be looking at a more involved question. It says here the following data refer to a four-cylinder internal combustion engine operating on a four-stroke cycle at 4,000 revolutions per minute. Now, before we begin, the 4,400 revolutions per minute, we can divide that by 2. And the reason is because it's a four-stroke engine. And we know that for every 2 revolutions, we only have one working cycle. So therefore, we can divide the RPM by 2. And then it says that the volume compression ratio is 7,6 is to 1. Okay, so I'm sure you all know what that means. Just show you quickly, illustrate here quickly with a syringe. When the cylinder is all the way at the top, we can say that's 1. And when it's all the way down at the bottom dead center, the volume then has increased by 7,6 times when it was at top dead center. All right, so that's what that is. Okay. Then it says that the diameter is, so the diameter of the cylinder, like that, is 78 millimeters, and the stroke, which is the distance that the piston moves, is 105 millimeters. The brake power is 38 kilowatts. The indicated power is 47.5 kilowatts. And it says here the air consumption is 21 kilograms. So 21 kilograms of air this engine sucks in from the atmosphere for every kilogram of fuel that is burnt. All right. So you need air and fuel in the in each cylinder. So all 4 cylinders, if you add those 4 cylinders up, the amount of air that it sucks in for every kilogram that is burnt of fuel is 21 kilograms of air. And then it says the fuel consumption is 13.6 kilograms per hour. So for every hour that this engine is running, the engine is burning up 13.6 kilograms of petrol or fuel. Then it says the energy released during combustion of 1 kilogram of fuel is 41,800 kilojoules. Okay, so that, just like with boilers, that is our calorific value. All right, so that's how much energy is released for every kilogram of fuel. All right, and then they say to us they want the mechanical efficiency. And that's very simple. We can go to this summary of the formulas that I gave you guys, and we can look for mechanical efficiency, which is over here, mechanical efficiency. And that's just the brake power over the indicated power. So remember, the indicated power is the power that's inside the cylinder, and the brake power is the power that is available to actually do work that's on the crank. All right, so that is comparing those two. All right, so all we need to do is mechanical efficiency equals the brake power, which is 38 kilowatts, over 37.5 kilowatts. And obviously, it's the brake power's always got to be less. It can never be more than the indicated power because of the losses, okay, the friction losses and whatever other losses is in the mechanical moving parts, right? And the mechanical efficiency then is 80%. 80%. All right. Then what they ask in the next question, point B, it says they want the mean effective pressure. Now remember, the mean effective pressure has to do with the indicated power. Okay, the indicated power which they've given us. All right. So the mean effective pressure, and that formula is on the top here by power. So indicated power equals, and we call it plane. Okay, so we got the mean effective pressure, the length, the area, the speed of the engine, and the number of cylinders, which is E. All right, so the power developed in the cylinder. So this is also, again, another very simple calculation. We're going to write there the indicated power equals plane. We got the indicated power, and we are looking for the mean effective pressure. We've been given the length, the stroke length. They gave it to us in millimeters. So they said here 105 millimeters. So we have to change that into meters. They gave us the diameter of the cylinder, which was 78 millimeters. So we're going to use pi d squared over 4 to calculate the area of the cylinder. So the area of the cylinder. So looking from the top, it's the area of the cylinder. Okay, then for the speed, again, we said that it's a 4-stroke engine. So we're going to be dividing the speed by 2. So 4,400 divided by 2. And then we also are going to be dividing it by 60 because we want it per second. Okay, so we divide that by 60, and then we're going to multiply it by the 4 cylinders. And then we're going to get the mean effective pressure. Right, so that comes out to 645.5 kilopascals. Right, and then we are at number C. Okay, now they want the volumetric efficiency. Okay, and it says refer to 1 atmosphere at, so 1 atmosphere we all know is 101.325 kilopascals, and at the temperature of 0 degrees Celsius. And we're going to convert that into Kelvin. So we know that is 273 Kelvin. Okay, so volumetric efficiency, what is that? Okay, so I'm just going to try and explain this with this diagram here, volumetric efficiency. So volumetric efficiency, it's on the sheet here as well. So here we have volumetric efficiency. And what that is, it's the induced volume per minute over the swept volume. Okay, so what does that mean now? So I've got this drawing here of the of one cylinder. Okay, the purple here, it's the piston at the bottom, right? And then we have the air intake port. So there's air coming in here. This is coming from outside, the atmospheric air, like they're speaking of at 0 degrees. So that is getting pulled in, okay? And this over here is the valve, okay? So this valve needs to open up. So it slides back, and then it opens up this area here as the cylinder is moving down to the bottom. And as it does that, it sucks in the air, okay? Then, at that time, the outlet port, the valve is closed at that point because you're trying to draw in air. The engine's trying to breathe in air. Right, so that valve is shut. Now, as you can see here, it pulls in the air, which is in blue, but it doesn't fill up the cylinder completely. You see the in red here. I've colored this in red because it just depends on the design of the engine and certain other factors, but mostly just think of it as the design of the engine. It pulls in air, but it cannot fill up the entire chamber or the entire cylinder with air. So what we have is the swept volume is what? The swept volume is the entire cylinder. It's the entire distance that this purple cylinder moves. So from the top, it goes all the way down. And that will include the blue area, which is, in this example, I'm just giving you now, 80% air that is pulled in from outside. And the rest of it is area inside that cylinder that didn't get air pulled into it. And obviously, if you wanted a highly efficient engine, you would want to pull this whole area full of oxygen, okay? But in terms of modern, or I would say normal road cars, they don't pull in 100% oxygen, okay? That's why we calculate in this volumetric efficiency to see how well it does this, how well it pulls in air to fill up the cylinder completely. Okay, so again, so the blue area plus the red area is the swept volume. That's the entire area of the cylinder, and we wish we could fill this whole area with oxygen, or air, I should say. Then the blue area is what we call the induced volume, okay? So that's what's coming from outside, the induced air that's going into the engine. That is the volume that is pulling air in to the cylinder. Okay, so think of it like this: when you breathing in to air into your lungs, you don't always fill your lungs to the capacity, and that's what the induced air is when you sucking air in, and we are comparing the air that is pulled in, the volume that is pulled in, the volume of air that is pulled in the blue, over the blue area plus the area that didn't get air sucked into it. So I hope that makes sense. So again, volumetric efficiency is the induced volume, the blue area, over the swept volume, which is the blue plus the red. Okay, so that's what we're comparing there. All right, so now that we have an understanding of what volumetric efficiency is, now we can continue with part number C of the question. Remember, volumetric efficiency, it's an example of that. When you're sitting still and you're calm, you're not breathing very deeply. Okay, you're not filling your lungs to capacity, so you're not inducing that much air into your lungs. But when you are running and you're highly exerting yourself, you breathe in very deeply, and you breathe in to try and fill your lungs with as much air as possible so that you can perform better. So we are just comparing, volumetric efficiency is comparing how well the engine is breathing. And if the engine is breathing well, the engine is performing well. So high performance engines, the volumetric efficiency is better. And normal road cars, the volumetric efficiency isn't as good. Okay, so induced volume, what we're sucking in, over the swept volume, the total volume that the piston is moving. So we're going to look for the induced volume first. All right, so we don't have that information of the volume that is induced, but what we do have is the mass of air that is pulled into the engine through the 4 cylinders for every kilogram of fuel that is burnt. And then we also have the fuel consumption per hour. So induced volume is in per minute, and the swept volume is per minute. So how we're going to calculate this now is by using the ideal gas formula, which we all know this by now. So on the formula sheet here, it says PV equals mRT. So that's a very basic elementary formula, the ideal gas formula, and we're going to use that. So we are going to be solving for volume. So do we have the mass? And we're going to first we're going to have to calculate what the mass is. Do we have R, the constant? We do. We have the constant there, 0.287 kilojoules per kilogram Kelvin. Do we have the temperature? Yes, we got the temperature. They said to us this is at 0 degrees, and we converting that to Kelvin, so 273 Kelvin. The pressure, they also gave that to us. It's atmospheric pressure, 101.325 kPa. Now the mass, how do we get that? So over here I've written the mass of air per minute. So they gave us the fuel, the amount of fuel that is used per hour. So how are we going to get that into per minute? We're going to divide that by 60. So we're going to divide 13.6 kilograms per hour. We're going to divide that by 60, and then we'll have that in per minute. So then we'll know how much fuel is used every minute, right? So 13.6 divided by 60, and we're going to get 0.226 kilograms per minute, right? And now, because we know the amount of air that is pulled in per kilogram of fuel, we can take the amount of air pulled in per kilogram of fuel and multiply it by the amount of fuel that is used per minute. So that's basically 13.6 divided by 60 times 21. So we calculated that to be 0.226 kilograms of fuel per minute times 21 kilograms of air per kilogram of fuel. And that's going to tell us that for every minute that the engine is running, the engine is sucking in 4.76 kilograms of air every minute. All right, so that's how much air is coming into the 4 cylinders every minute. All right, and we're going to put that in there, and then we can solve for the volume. All right, so the volume. And now we have the induced volume, which is 3,681 meters cubed per minute. So that's the volume that is being induced. So that's the top value here that's being pulled into the cylinders every minute. All right, now how do we get the swept volume, which will be the total? You can see the blue plus the red. So the swept volume now, so I've made that in red. It's going to be the area of the cylinder, pi d squared over 4, times the length of the stroke, which they gave us as well, times the number of working strokes, and remember that's going to be 4,400 divided by 2 because it's a 4-cylinder engine, times the number of cylinders, which is 4 cylinders. And you're going to see that swept volume is greater than the induced volume. So that's going to be 4,42 meters cubed per minute. Okay, and that's what we expect. If the volumetric efficiency was 100%, both these values would be the same. But because it can't pull in, this particular engine can't pull in to fill the entire cylinder, the whole entire swept volume with air, it only induces a certain portion with air. The induced volume is less. So now we can calculate what the volumetric efficiency is. So that's it's 3,681 meters cubed per minute over 4,42 meters cubed per minute equals 83.28%. Okay, so that is the effectiveness of the breathing of this engine. All right. The next part of the question is it's asking for the brake thermal efficiency. Okay, the brake thermal efficiency. So if we go to the sheet again, it says here the brake thermal efficiency compares the crank to the fuel. Okay, so the power that's on the crank to the amount of power that we're getting from the fuel. So that's the brake thermal efficiency. Okay, and I'm just going to go to the example for this one. Yeah, so here we are, part D, brake thermal efficiency equals the brake power, which was the 38 kilowatts, over the energy from the fuel. So we say 13.6 kilograms that we were burning per hour. We want that in per second. So we're going to be dividing that by 3,600 times by the calorific value. And there we have the brake thermal efficiency. And remember, this value needs to be low because internal combustion engines are not efficient. So of the total energy that you get from the fuel, only 24% of that energy is actually used for actual work, to turn the crank, to actually put power on the road or whatever. Okay, so very little. And a huge amount is lost. All right, now they want on part E, what are they asking for now? They're saying the brake thermal efficiency ratio relative to the air standard cycle. What does that mean? Okay, so the air standard cycle. So at the top here, we got air standard cycle or air standard efficiency. And this is the ideal the ideal thermal based on the Otto cycle. Okay, so this is a perfect scenario. Okay, so what should that efficiency be? Over, so that's going to be, sorry, it's going to be the brake efficiency. So let's go to it here. Where am I? Yeah, the brake ratio. It compares the actual to the ideal. So the actual brake efficiency, which we have calculated up here, the brake thermal efficiency, over the ideal, which is the ideal is the air standard efficiency. Okay, so how do we do that? Also very simple. It's just the two formulas. We've already calculated the brake thermal efficiency over here. Now we just need to calculate what the air standard efficiency is, and that's this top formula. So we plug in the values here, and by gamma we're going to put 1.4 because it's ideal, and we're going to calculate what the air standard efficiency is. You can see that's much higher. The ideal is 55.57%. And then all we do is we compare the two, the brake thermal over the air standard efficiency, so 24,06 over 55,57, and then we get the brake thermal efficiency ratio. So those are just easy to just plug into the formulas, and we get the answers. So I know it's a more involved question. It's a very, very good question, and I want you guys to carefully go through this, think about it, and let me know if you need any help.